Hey there, and welcome. We run into acids all the time. The tartness in a lemon, the fizz in your soda, they're literally everywhere. But how much do we really understand about what they are and what they do? Well, today, we're going to pull back the curtain and dive into the secret chemistry of acids. I bet you've seen this a million times. You've got an upset stomach, so you drop an antacid tablet into a glass of water, and you get that awesome, satisfying fizz. It's a classic fix. But have you ever stopped to think about what's really happening in that glass? It looks pretty simple, right? But that fizz is actually a huge clue. It's telling a much bigger story about how acids and their opposites, which we call bases, actually interact. So to really get what's going on in there, we gotta take a step back and figure out what makes an acid, well, an acid. Okay, let's get right into it. It turns out that pretty much all acids, from the super powerful stuff in a car battery to the gentle citric acid in an orange, they all have a few signature moves, a few key reactions they always do. Let's take a look at the three most important ones. First up, if you take an acid and you mix it with a reasonably reactive metal, you're always, and I mean always, going to get two things out of it: a salt and hydrogen gas. And here it is, happening right in front of us. The acid is literally eating away at the metal, and all those bubbles you see, that's pure hydrogen gas fizzing away. That fizz is the dead giveaway that this reaction is happening. Now, here's something that might surprise you. When a chemist says salt, they're not just talking about the stuff you put on your food. It's a whole family of compounds. And the specific kind of salt you get all depends on which acid you start with. So if you use hydrochloric acid, you get chlorides. If you use sulfuric acid, you get sulfates. Nitric acid, you get nitrates. See the pattern? All right, on to signature move number 2. And this one's a big deal. When an acid comes face to face with its chemical opposite, a base, they do something called neutralization. And what do you get? A salt again, but this time the other product is just plain old water. Whoa, just look at that incredible color change. We're starting with this black, solid base. It's called copper oxide and an acid. And when they react, boom, you get this beautiful blue liquid. That blue stuff is the salt, copper sulfate, that's now dissolved in the water that was also created. It's just a fantastic visual proof that a brand new substance has been made. And that brings us to our third and final key reaction. When an acid reacts with something called a carbonate, it produces a salt, water, and something extra, carbon dioxide gas. Now, does that sound familiar at all? And there it is. This is the secret to our fizzing tablet from the beginning. Those antacid tablets are packed with carbonates, like calcium carbonate. When they hit the acid, they create that fizz we all know. But this time, the bubbles aren't hydrogen, they're carbon dioxide. So, mystery solved. Okay, so we solved the mystery of the fizz. But wait, there's more. You might think that a strong acid is just one that's super concentrated, right? Well, the truth is actually a bit more interesting than that. The real difference between a strong acid and a weak one all comes down to how they act in water. The key idea here is a word you might not know: dissociation. Now, it sounds complicated, but all it really means is the acid molecule literally breaking apart when it hits the water. And when an acid dissociates, it unleashes those all-important hydrogen ions. You can kind of think of it as the acid releasing its power into the water. So here's the breakdown. A strong acid, like hydrochloric acid, is an all-or-nothing kind of acid. It completely dissociates. I mean, every single molecule breaks apart and releases a hydrogen ion. But a weak acid, like the ethonic acid in the vinegar in your kitchen, it only partially dissociates. Just a tiny fraction of its molecules actually release their hydrogen ions. So even if you have them at the exact same concentration, their acid power is totally different. And this slide, wow, this says it all, doesn't it? We have two acids, same concentration, same piece of chalk. On the left, you've got the strong acid, and look at it go. It's just tearing through that chalk because of all those hydrogen ions. Now look to the right. The weak acid is reacting so much more slowly. It's the perfect picture of the difference between complete and partial dissociation. Okay, we have all the clues. We know what acids do. We know what makes them strong or weak. So now, let's put it all together and take a really close look at that process of neutralization. So in any neutralization reaction, you've basically got two main characters in the story. From the acid's corner, you get the hydrogen ion, H+. And from the base's corner, you get the hydroxide ion, OH-. At first, they're just swimming around separately in the solution. And here's where the magic happens. That H+ ion from the acid finds the OH- ion from the base, they combine and they form H2O. That's right, just a stable, neutral water molecule. They've essentially canceled each other out. And this simple little equation you see here, that is the heart of it all. This is the core reaction for every single acid-base neutralization. It doesn't matter if it's a strong acid or a weak one, deep down at the ionic level, this is what's happening. The whole point of neutralization is just to make water. So why does this matter so much? Because we use this reaction everywhere. It's in the antacid tablet neutralizing stomach acid, it's farmers adding lime to fix acidic soil so their crops grow better, it's scientists adding lime to lakes to fight acid rain, and it's even in the toothpaste you use every morning to neutralize acids from food. Neutralization is happening all around us, all the time. We've covered a lot, but there's one last piece of the puzzle. One simple, really elegant idea that connects everything we've just talked about. And believe it or not, it all comes down to a tiny particle you've known about for years, the proton. Okay, let's think about this for a second. What is a hydrogen ion, that H+? Well, a normal hydrogen atom is just one proton and one electron. That's the whole thing. So if it loses its only electron to become an ion, what's left? Just a single proton, which means we can define an acid in a much more fundamental way. An acid is simply a proton donor. And if an acid is a proton donor, well, it only makes sense that a base has to be a proton acceptor. And that's it. That's the whole game. All that complex chemistry we saw, the fizzing, the color changes, the neutralization, it all boils down to this simple, elegant exchange of one tiny particle. It's pretty incredible when you think about it. This tiny little handoff of a single proton is what helps keep our bodies and our entire planet in balance. It really makes you wonder, doesn't it? What other simple, elegant rules are out there, quietly running this incredibly complex world all around us?